in this module we will begin analyzing waveguides that we discussed in the previous module. For the sake of simplicity, we will consider only rectangular waveguides, which means that they have this cross section which is rectangular. So if you look at the cross section, this is how they would look. Probably let us make it more rectangular rather than square. So along x axis, along y axis, the width of the waveguide is A and the height of the waveguide is B. Okay. In the traditional notation, the width is actually taken to be larger than the height. Okay. And we will see why that has to be done, although in principle there is no difference between width and height. I mean, you can consider B as width and A as height, and that doesn't really matter. Okay. We will make one important assumption, that is, all the field quantities, electric fields that are there and magnetic fields, they would all have to propagate along z axis. Okay. So they would be propagating along z axis, but they could be varying with respect to x, y, and in the other case they might also vary with respect to z. For the rectangular waveguides though, we can assume that the electric fields would vary along with respect to x and y, but they would also propagate along z. Now what sort of propagation should we assume about this one? Should we assume a cosine propagation, sine propagation, a pulse propagation? Well, what we will do is we will assume that these waves are of a particular frequency, okay, and they are propagating in the medium in which they can suffer both attenuation as well as just a propagation. So they can suffer attenuation as well. Okay. So we capture that by writing down the propagation constant to be a complex number consisting of alpha and beta as real and imaginary parts. As we have seen, even for the transmission line case scenario, alpha corresponds to attenuation, beta corresponds to propagation constant. And the propagation of all these fields, this should have been Hy, okay, so I forgot Hy. So all these field components would be varying along e to the power minus gamma z, and even the components Ez and Hz, they both would be varying as a function of e to the power minus gamma z. Now the advantage for assuming this type of a propagation is that I can replace the derivatives of any of these field quantities with respect to z by minus gamma times the field quantity. So in other words, I can replace the differential operation by a simple multiplication operation with minus gamma. Okay. The starting point for analysis would be the two Maxwell's equation which relate the curl of electric field and curl of magnetic field to each other. Okay. In the second expression, in the curl for H, we have ignored whatever the conduction current is, because we are going to assume that the region of interest for us to look at the waves is inside the waveguide, and inside waveguide there is no conductor and there is no possibility of having a conducting current. Okay. Well, if there is no current, then how are these fields generated? Well, the answer is that the currents are there, but they are not there inside the waveguide, but they are there on the waveguide walls. We will also of course assume that the material that fills this waveguide is all completely perfect in the sense that there are no leakage currents. Therefore, we can assume safely that there is no currents inside the waveguide, and anyway these are hollow cavities, and for the voltage ranges that one chooses, there would essentially be no leakage inside the air dielectric, and hence there won't be any current inside, the conduction current won't be there. So whatever the current that would be there, that would be displacement current, and I have also replaced, or I am actually using without telling you, that these are phasor quantities, right. So I am not explicitly indicating the time dependence, we are only interested in the spatial dependence, because time dependence is taken to be the phasor form. So del by del t becomes j omega, integral becomes 1 by j omega, and because of that reason we have changed, we have written this as j omega. We will also assume that mu and epsilon are constants, okay, unless we specify them to be non-constants. Okay. We also know how to obtain curl of electric field. This is simple determinant of this 3 by 3 matrix, and fortunately this works only for, unfortunately this works only for the rectangular waveguides, and that is probably the reason why we are choosing to work in the rectangular field waveguides, because the formulas are little tractable compared to the rectangular waveguides. Although there is nothing specific, there is nothing special about a rectangular cross section. In fact, circular cross sections are much more widely used than rectangular cross sections in several applications. Okay. So going back to the rectangular cross section, we have this curl of electric field consisting of three different components, x component, y component and z component, and this should be equated to the right hand side. The right hand side also contains three components, hx, hy and hz, all these components getting multiplied by minus j omega mu, right. So this curl of E must actually be equal to minus j omega mu h, so which means that it should be x hat minus j omega mu hx plus y hat minus j omega mu hy plus z hat minus j omega mu hz. Okay. Unlike the plane wave situation, none of these hx, hy are going to be 0, none of these hz won't be 0, ez won't be 0 in general, and moreover hx and hy will not be independent of x and y, so you can't just remove them out like that. They do depend on x and y, okay, because there are bounding boxes, if you think of this, along x direction as well as along y direction. There are conductors. If you go along x, there are two conductors. If you go along y, there are two conductors. Of course they are not really two conductors, but there is a single conductor, but there is a sort of imagination that there are two conductors out there, okay. You can think of that way in that. Okay, now here are a set of equations which I have written, okay. This set of equations are obtained by equating the appropriate or writing down the curl expression for electric field as well as curl for the magnetic field, and then equating them correctly, okay. So equating them to the corresponding components. So you can see that the first three set of equations are simply this equation, curl of E is equal to minus j omega mu, because minus j omega mu hx must be equal to del Ez by del y, you can see here, minus del Ey by del z, but I already know what is del by del z. Del by del z is minus gamma, and there is a minus sign already present here, so that becomes plus gamma Ey. I hope you understand this first equation carefully. Look at these two, so maybe I can help you in that one by erasing off this part. Okay, you can rewrite that one, minus j omega hz. Now consider each component, okay. So consider for example this component and then equate that to this one, okay, and then replace del by del z by minus gamma, and you will actually get the first three equations. Similarly, writing down curl of H, you will get the next three equations. I really urge you to write down these equations, without looking at the answers first, and then write down them and convince yourself that this is all right. Now you may ask, why am I doing this? What is the need for doing this? That turns out that I can actually solve for the electric and magnetic fields by expressing all of them, the transverse components. What are the transverse components? Transverse components are x and y components for the electric field in terms of Ez and Hz. These Ez and Hz are called as the longitudinal components, okay. So you have three axes, right? So this is the z axis, this is the x and y. Don't worry if my notations are not really consistent. What I want to show is that there are three axes out there, and the electric field components in the x and y axis together are called as the transverse component, and the component of the electric field along this one is called as the longitudinal component. So in the plane, okay, so the electric field that you will have will be called as the transverse component, and therefore the total electric field can actually be split into transverse and longitudinal components, okay. Longitudinal, only Ez is there. Similarly, you can split H as well into its transverse and longitudinal components, okay. So I want to express Ex and Ey in terms of Ez and Hz. I also want to express Ht, that is transverse components, as some function of Ez and Hz, okay. Some function, let's say this is g function g, okay. So if I express them, then if I know how Ez and Hz are to be solved, then once I have that, I can find out the expressions for Ex, Ey, Hx and Hy from these two solutions, right. So only two variables Ez and Hz need to be known in order to completely specify Ex, Ey, Hx and Hy. Again, there is no specific reason why one has to choose the horizontal components, except that for the mode nomenclature it becomes easier for us to talk of TE or TM modes if I know Ez and Hz, right. So for a TE mode, there won't be any component of the electric field along the longitudinal, so Ez will be equal to 0. Then you are left to solve only for Hz and use that to obtain the transverse electric and magnetic field components, okay. Now how do we do that? Consider for example this second equation. Okay, so let me highlight that equation. Okay, I use this equation to solve for Hy. What do I mean by that? I simply take this minus j omega mu onto the left hand side and then write down what is Hy. Okay, so you can see Hy is actually equal to gamma by j omega mu Ex, okay, by taking minus 1 by j omega mu down, and you also have plus 1 by j omega mu del Ez by del x. I don't know how Ez varies with x, I only know how Ez varies with z. I also know how Ez varies with the other, I only know all the other components varying only with z. I don't know how they vary with x or y, okay, but doesn't matter. Now I know what is Hy. Is there Hy in the other group of equations, right? So there is Hy in this equation wherein you have del Hz by del y plus gamma Hy is equal to j omega epsilon Ex, okay. And if you look at Hy is expressed in terms of Ex and Ex and Ez. So if I can write down this, substitute for Hy into this expression and rearrange it and pull this gamma by j omega Ex to the right hand side, then I will have Ex solely in terms of Ez and Hz, okay. So I can do that. Let me try doing that one. I cannot use this second equation because I don't know how Hy would vary with x. If I try doing that one by taking the derivative with respect to x, then I will also have to write down del Ex by del x, and this becomes a second order equation, del square Ez by del x square. So I don't know how to do that. Therefore I don't use this equation, and there is no Hy in the second equation, and there is only one Hy in this equation which I can use, okay. So let me use that equation and write down substitute for Hy. So what do I get? I have del Hz by del y, that hasn't changed, right, plus gamma square by j omega mu Ex plus gamma by j omega mu del Ez by del x must be equal to j omega epsilon Ey, right. So with this I can actually pull this gamma square by j omega mu epsilon to the, this is actually Ex, right. So this is Ex, not Ey, okay. So I can pull this onto the right hand side and then pull everything onto the left hand side, rearrange the two equations. What I get is j omega epsilon minus gamma square by j omega mu into Ex must be equal to gamma by j omega mu del Ez by del x plus del Hz by del y. I can rearrange this equation in the brackets, expression in these brackets. So I get minus omega square mu epsilon plus gamma square, okay, times Ex must be equal to j omega mu gets multiplied. So I have gamma del Ez by del x plus j omega mu del Hz by del y, okay. Call this omega square mu epsilon plus gamma square as H square, okay. So H square is equal to gamma square plus omega square mu epsilon, okay. So if I call this as H square, then Ex will become minus gamma by H square del Ez by del x minus j omega mu by H square, this is H square, times del Hz by del y, okay. I can of course pull this minus sign outside and then call this H square as a common factor. So what I get is minus 1 by H square gamma del Ez plus j omega mu, right. So this is what I get for Ex. So it is very clear that Ex has been expressed in terms of, or proportional to some functions of Ez, and this is Hz, right. So our objective has been achieved for Ex. Now you have to do this procedure for Ey, Hx, Hy. Rather than doing all of that, I will simply give you the values. You can actually check for yourself. You all you need to do is to find a corresponding component and then find another equation, substitute, rearrange all that equations, and you will be able to obtain what is Ey. Okay, you will be able to obtain what are all the different terms, but I will just write down for Ey. Okay, that would be gamma del Ez by del y minus j omega mu del Hz by del x. Okay, so this is one expression for Ey. Similarly, I have expression for Hx as well as Hz. These are given in the textbook, so you can refer to that. Minus 1 by h square minus j omega epsilon del Ez by del y, okay, plus gamma del Hz by del x. Finally, you have Hy, right? Hy is minus 1 by h square j omega epsilon del Ez by del x plus gamma del Hz by del y. Okay. So with all these things known to us, right? So with all these fellows expressed as some function of Ez and Hz, let's actually write down the wave equation for Ez, write down the wave equation for Hz, solve them, and then use those expressions in these expressions for Ex, Ey, Hx and Hy, okay, to obtain, right. So once you have done that one, all you have to do is to substitute for Ez and Hz after calculating them and substitute and obtain the values for Ex, Ey, Hx and Hy. So the objective of getting the transverse components in terms of longitudinal components and the relation between the two has been achieved. Okay, what do we do from here? Where do we go from here? First of all, let us see what possible modes that we can obtain. Okay, so let us first try if any way we can obtain TEM mode. Well, what do we need to obtain for a TEM mode? In TEM mode, you have Ez equal to 0, Hz is also equal to 0, right? So this is the TEM mode, right? For this mode in which both Ez and Hz is equal to 0, what will happen to del Ez by del x or del Ez by del y? What will happen to these components? They would all go to 0. So all the components that are mentioned in these brackets will have to be equal to 0, and if you want a non-zero value of Ex, Ey, Hx and Hy, the only way you can obtain that is to make h square is also equal to 0. Okay, because you now have 0 by 0, and that 0 by 0 will make a small quantity by small quantity will keep everything to be finite. So if you want Ex, Ey, Hx and Hz and all of them to be independent of x and y and propagating along z, which forms the TEM mode, then the condition is that h square should be equal to 0, or equivalently h is equal to 0. Now h equal to 0 means gamma square must be equal to minus omega square mu epsilon, which also means that gamma must be equal to j omega square root mu epsilon. We know that this is alpha plus j beta. This simply implies that alpha is equal to 0, beta is equal to omega square root mu epsilon, or omega by v. Okay, so we have seen this condition, for a TEM mode. This is what you need to have. A lossless TEM mode condition is required for the waves to be existing. Of course, this does not really happen for a waveguide, so you can conveniently and safely scratch this off from your list of allowed modes. So then what about other modes? Can I have TE modes? It is possible. For TE modes, Ez must be equal to 0, and what will happen to Ex in this case? Ex will be minus 1 by h square, right? Ez component is 0, so j omega mu into del Hz by del y. So you get minus j omega mu by h square del Hz by del x. Similarly, you can write down what is Ey, okay, and write down what is Hx and Hy, okay. You will actually see that Ex and Hy pair can be formed, okay, Ey and Hx pair can be formed just as you would form in a plane wave scenario, okay. Can I have TM modes? Certainly possible. So for TM modes, all that we need to ensure is that Hz is equal to 0, and then Ex, Ey, Hz, Ex, Ey, Hx and Hy will simply be functions of Ez itself, okay. So this is also possible. So since we are not writing down the expressions, let me write down this over here. TM modes implies that Hz is equal to 0, and these are also valid mode patterns for us, okay. Now we need to solve the equations, okay, because all we have done so far is to establish that we can write down Ex, Ey, Hx and Hy in terms of Ez and Hz, and then we can characterize the modes, that is possible set of solutions of this Maxwell's equation in this waveguide problem to have two types of modes, TE modes and TM modes. Okay, so for these modes we need to actually obtain what is Ez and Hz. Okay, but before we do that one, we need to first of all obtain an expression for Ez itself. Okay, how do I do that? Well, that is actually quite simple, right? I know from Helmholtz equation, right? I know from Helmholtz equation that del square Ez for any component of the electric field or magnetic field, I can write this Helmholtz equation. So del square Ez plus k square Ez must be equal to 0. What is del square here? Del square is nothing but the Laplacian operator operating on the component Ez. What does a Laplacian operator consist of? Del square by del x square, del square by del y square, and del square by del z square. So this particular operator has components for x, y and z, or rather has differential operators with x, y and z. Okay, x and y are transverse, z is the longitudinal one. In fact, I can split this del square itself into del transverse and del longitudinal. Okay, now there is no inherent advantage of doing this, but this is something that you would find in microwave literature quite often. So transverse component of the Laplacian is given by del square by del x square plus del square by del y square. The longitudinal component is actually del square by del z square, which is nothing but minus gamma multiplied by itself, because remember each del by del z constitutes a minus gamma. So multiplying this one, what you get is gamma square. Okay, so this equation can actually be rewritten in terms of its transverse components, transverse Laplacian del transverse square Ez plus gamma square plus k square. Ez is equal to 0. Okay, so this is what we wanted to write down, but I already know what is k square, right, because I have this waveguide, right, which is filled with mu and epsilon materials. I know k square must be equal to omega square mu epsilon, correct? Since I know k square is equal to omega square mu epsilon, I can substitute for that, and I remember from this earlier slide that gamma square plus omega square mu epsilon is actually h square. So what I get effectively is that del transverse square Ez plus h square Ez equal to 0. A similar equation can be obtained for Hz as well, plus h square Hz is equal to 0. Okay, so these are the two equations which are obtained from the Helmholtz equation, which we will use as a starting point for understanding TE and TM modes. Okay, so we will use this one. Of course, the way that we would be solving these problems would be to write down the general expressions for Ez if you are solving for TM modes, or if you are solving for TE modes, you write down the expression, use the expression for Hz and then write down the solution for Hz. Now it's not just enough to write down the solutions, you also need to satisfy the boundary conditions, right? So that would be the next step. So write down the solution for Ez or Hz depending on which mode you seek, and once you have obtained the general solution, you then need to go to boundary conditions and apply that and then obtain the corresponding expressions. Okay, so let us assume that we want to deal with TM modes. For TM modes, Hz is equal to 0, so I need to solve for Ez, right? So solve for Ez. Okay, so I'll split this up. I say del square by del x square Ez plus del square by del y square Ez plus h square Ez is equal to 0. Okay, so this is a second order partial differential equation in two variables. Now it's quite difficult to solve partial differential equations in one variable. Now we have two variables to solve. How do we proceed? Fortunately, this problem has been studied quite a bit by the mathematicians, and they have come up with various techniques. One of the techniques that you can use is what is called as separable variable method, or sometimes called as variable separation method. Okay, in variable separation method, what we assume is that whatever the solution that we are after solving for Ez, which will be function of both x and y, obviously, right, this is a function of both x and y because the partial differential equation has both components. So this can be written as x of x, y of y. Okay, and del square by del x square will become x double prime of x times y of y, because this is partial derivative with respect to x. So when you differentiate twice, you get x double prime of x, y doesn't really get changed. Similarly, del square by del y square becomes x of x, x is not being operated on, y gets operated twice, so this becomes y prime of y, okay, where x prime of x is nothing but d square, the total derivative, d square x by d small x square. You could have chosen this as f of x and g of x and everything would have been the same, except that in place of capital X you would have f and capital Y you would have g. Okay, so this is the equation and we already know how what is del square by del x square look like. So I can substitute for this. So to obtain x double prime y, I am not writing the x and y dependence, that is kind of understood over here, plus y x y double prime x, okay, plus h square xy. Remember, Ez is equal to x into y. So this is equal to 0. Divide everywhere by xy. So if I divide that one, I get x double prime by x plus y double prime by y is equal to minus h square. Okay. Now here is where the thing which really comes up over here. What this actually equation is telling you is that there are two components. So let's just do this one first and then go to that minus h square thing. If you look at this expression, this is very critical expression and contains heart of the variable separable method. You have a function which is completely of x, okay, and then you twice differentiate it, divide that one by the original function x, okay. So for example, you can have this your x of x, okay. So you differentiate this function, so maybe the function differential would come, first differential would be something like this, second differential would be something like this, okay. I am not really interested in finding out this, but what you have is x double prime by x is a quantity that has to be specified for all values of x. Similarly, you can actually have a variation of y with respect to y, so maybe that is varying like this, the first derivative would vary this way, the second derivative again would vary in this way, okay. So this is your y double prime. Again, at each point on y, you have y double prime by y, okay, that could possibly be changing. H square for a given value of omega mu epsilon would be a constant, because this is equal to gamma square plus omega square mu epsilon. So this is a constant. Now you have one function which is varying with respect to x, you have one term which is varying with respect to y, and one constant, all of them equal to 0, right. So if all of them are to be equal to 0 and this is a constant, the only way this can happen is that these two terms, right, x double prime by x and y double prime by y also must be constants, such that three constants are summing to 0. This is the crucial point. Even though your x of x could be a function that is varying, y of y that is varying, the corresponding ratios that you take would then have to be constant. X double prime by x is a constant, y double prime by y is a constant, and h square is a constant, and the sum of these three constants must be equal to 0. Accordingly, let us call this x double prime by x as some kx square, y double prime by y as ky square, okay. So let's call this as minus kx square and minus ky square, so it becomes easier for us to substitute into the original expression. So substituting this into original expression, you get minus kx square plus ky square, of course, plus gamma square plus omega square mu epsilon is equal to 0. Remember, here kx and ky are constants. Gamma is the one which we are after. So gamma square will be equal to kx square plus, or rather it would be equal to omega square mu epsilon, right. So gamma square plus omega square mu epsilon is what we had considered as h square. So I need to actually push this one out, right. So it would be kx square plus ky square minus omega square mu epsilon, okay. So this is omega square mu epsilon. So if I know epsilon, if I know mu, and if I find out kx and ky, then I can find out what is gamma, okay. So in the next module we will start solving these equations and show you how the electric and magnetic fields would vary with respect to x and y as well as along with z. Thank you.